I don't know if you've taken the time to read Dr. Garfinkel's bio, but just incredibly impressive. But he comes to us from the Census Bureau, where he is the chief computer scientist on data privacy. And I just want to point out one point in his bio. He is the author of 14 books, but one of those books was Database Nation, The Death of Privacy in the 21st Century, which was published in 2000. So it's a great honor to have Dr. Garfinkel here, and I know that it was hard for him to get here, so please help me welcome him, and we look forward to his talk.
So thank you. So I'm going to talk about the 2010 census and the 2020 census. I'm going to talk about why the Census Bureau is moving to differential privacy. I'd like to thank you all that are here for staying this long. I promise that there'll be very little, like no mathematical equations. There will be a graph. So the motivation is the Constitution. In Article 1, Section 2, it's talking about what the House of Representatives, you can't read that text, but it does say that the actual enumeration shall be made within 3 years after the first meeting of the Congress of the United States, and within every subsequent term of 10 years in such a manner as they shall by law direct. And that's why we do a decennial census. And thankfully, the first census was done in 1790 by Thomas Jefferson, so that in this country, the censuses are always in years that end with a 0 to make it easy for me. But in such a manner as they shall by law direct, as Congress passes a law. And they passed Public Law 94-171 back in 1975, which explains how the census is supposed to be done. And then we put out a Federal Registrar notice in 2017. Now, this was a notice for the 2018 end-to-end test. And in the end-to-end test, we said that we were going to report by block the number of people by race and ethnicity, the number of people over 18, the occupancy status, so how many occupied houses there are in each block, and the group quarters population. So we do a population, we do a census of housing units, of residences, and of group quarters. And a group quarters is anywhere where people are living together and they're not in a family. So like a college dormitory or a military barracks or a prison. But we also have to protect privacy. Title 13 of the US Code covers the Census Bureau, and Section 9 talks about the fact that our information is confidential. And it says that we're not allowed to publish any information in which you can determine the person who provide, or the establishment that provided the information in our data product. So that's really simple. We have to publish data that's usable, and you can't identify the data from specific individuals. So I'm going to tell you now what we did in 2010. And apparently I'm going to get finished really early. So in 2010, if you were a householder, you got this form. Does anybody here remember filling out the 2010 census? That's amazing. I don't, actually. This form is the official form for all people at this address. We filled it out by house, and it's easy and quick, and your answers are protected by law. And here are the overall counts. We counted 308.7 million people in 2010 and 116.7 million households. On 10.6 million habitable blocks, and for each of those people, we reported aggregate data for sex, age, race, and ethnicity, the relationship to person one. So if you build a histogram of the United States and you ignore the high resolution data, because that's actually a different set of tabulations, it's a histogram with 492,000 boxes for the whole country. But we actually then report that same histogram all the way down to the census block. So if you take the total of how much data we published, we published around 7.7 billion statistics for 2010. And that's about 25 statistics per person. Now, we collected sex, age, race, ethnicity, in relationship to person one. So that comes out to about 6 statistics per person. And we published 25 per person. So if you know any math at all, then you realize that you can create a system with 25 billion simultaneous equations and roughly 1.8 billion unknowns and solve and get get a solution that matches our published statistics. We call that database, I'm getting ahead of myself. We call that database reconstruction. We'll come back to that. So, so in 2000 and 2010, this is the way we make statistics. We calculate, we ask people questions, and we create this thing we call the Census unedited file. And those are the counts that go to Congress for reapportioning the House of Representatives. And then we edit it. I was shocked. We edit your returns. And we create the census edited file because people make mistakes and we fix them. And like you might say that you live with your mother and your daughter and your mother's 6 and your daughter's 66. So we'll swap them. We did these things which I have labeled confidentiality edits. And we created something called the 100% detail file. And then we use that to make the official tabulations. So the problem is, like, there are blocks that only have one family living on them, and so they would be highly identifiable. And so what we did in 2000 and 2010 was we took these highly identifiable families and we swapped them with some other family somewhere else in the state. And the advantage of this swapping is that it's really easy to understand. It doesn't affect the counts if you only swap within a state. You can run it state by state, and the operation's invisible to the rest of the census processing. And in fact, less than a handful of people in the Census Bureau understood how the 2010 swapping actually worked. So the disadvantage is it doesn't consider or protect against database reconstruction attacks. The privacy protection is not quantified. The swap rate and the details of the swapping must remain secret. It's in small text, maybe because we're unhappy about that. So we don't tell people how we swapped. And the privacy guarantee is based on the lack of external data. So we know that the disclosure avoidance techniques we used in 2010 were flawed, but they were the best available techniques that we had at the time. It assumed that if we applied this to one data product and then another data product, that the results of those two systems would be compatible. That, like, we could make a lot of data publications from the confidential data without compromising the privacy of the confidential data. And I think I explained that that's not true. So we released exact counts by block and tract and county level. We actually said there are this many people on every block, and there are this many people of each race on each block. We gave the ages of those people to within 3 years on every block, and to within 1 year on the tract. We released exact counts for sex, exact counts for relationship to the household. We published a lot of data. What we've done is, I explained this database reconstruction. We've actually done it at the Census Bureau. We've taken the 2010 data that was published, and we've reconstructed the microdata from the published statistics. So it was a lot of work. I was involved in that project. We're writing it up for a scientific journal. It's very exciting, and it's really frightening. So this was readable on my system, but this is why I like sending people PDFs and not... you can't read that, but I'll read it to you. We confirm that the microdata from the 2010, the confidential 2010 100% detail file can be reconstructed accurately from the PL94 and the balance of SF1. So we actually did an accurate reconstruction from which we can regenerate all the published statistics. The block geocodes are always correct, as is the voting age. And I can tell you that 50% of the reconstructed records match both the swapped data file and the unswapped file, which is a real problem. So I can tell you that more than 70% match exactly if you allow age within 1 year. So sometimes, we collect age 2 different ways, by your date of birth and by how old you say you are. So we always match within 1 year. 90% match if you allowed an error in age, sex, or race. More than 50% of the confidential records are unique on the block. And more than 35% of the reconstructed records are population uniques on the same record. So there's a lot of statistics there. What does that mean? It means it's really bad. It means that with the data that we published with 2010, you can learn a lot of private information about people in the United States that we said we wouldn't publish. A lot. A lot. But that's getting cheaper, right? So this was a project that took maybe 10 PhDs and maybe like a whole bunch of clusters on Amazon for maybe like 3 or 4 months. But that means that you now know how to do it, so you could do it with maybe 4 graduate students for maybe a year. And that means that like in 5 years, maybe it's an undergraduate research project. And in 10 years, it's like a high school science fair project. And that's the problem, right? So earlier, I'm going off script. Earlier, there was this slide about the Census Data Research Study Group or something. That was not a US government group. That's a group of people at one of our data users. And they don't understand why we're moving to differential privacy. The reason we're moving to differential privacy is because we're legally required to do so, because we cannot keep publishing data from which you can reconstruct confidential data. And that's just the law. There's no choice. There's no backup plan. So let me tell you what we're doing for 2020. In 2003, these 2 people, Irit Dinar and Kobe Nissim, they started looking at this problem of database reconstruction. It's been looked at for years. It's been called query auditing. The idea of having interactive databases that would give you queries on confidential data, that goes back to the 1970s. And there was this proof in 2001 that if you are the database owner and you're looking at these queries that are coming in to see if the combination of all these queries can overcome your privacy mechanism, that turns out to be something that's called NP hard, which means it's exponentially difficult. You have to look at all the previous queries. It's just too hard. So what Dinar and Nissim did was they said that instead of doing query auditing, we can just add noise to the results, and we don't have to worry about database reconstruction. And in 2006, Dwork, McSherry, Nissim, and Smith, they actually came up with these nice formula that tell you how much noise to add to come up with the privacy outcomes that you want, and we call that differential privacy. It's a generic approach for protecting privacy by adding noise. And so the key thing that noise does is it creates uncertainty. You can still do database reconstruction, but you don't know if the database that you've reconstructed is the correct database. That's all there is to differential privacy. It gives you a lower bound on the amount of noise that you have to add for a particular privacy outcome, and it gives you an upper bound for the amount of privacy loss that's going to result from your publication. And the cool thing is that the mechanisms are composable, so you can put together a privacy system with these building blocks, and the math that you do, the reasoning all works. And that's why we can use differential privacy for the 2020 census. So in 2017, we announced that we would be using differential privacy for the 2020 census because it gives us this provable bound. Now, this is a graph. We call these ROC graphs, or don't worry about that. But basically, this is the privacy loss. And here, the measurement is this value called epsilon. And here we run it from 0.25 to 10. And the accuracy here, we show that as you increase the privacy loss, the accuracy of the results that are published gets better. Now, one of the funny things about the literature of differential privacy is that the authors, like Dwork, always says, well, that decision about what epsilon should be, that's up to policymakers. And then they go on to say, but we assume that epsilon's less than 1. Right? Well, if it's up to policymakers, you can't assume that it's going to be less than 1. I'm going to give you a little bit more background now, because it got too complicated all of a sudden. So here's like a typical census block. This is a fictitious block. It's not a real block. And here we collect data. There's like 10, oh, this is the real data. This is like there's 10 people under 18 who are male, and 20 people who are under 18 who are female, and 40 people who are over 18 who are male, and 30 people. You don't have to remember that. So, oh, this is another block. So anyway, this is the as reported. So this slide's just wrong. This one over here, ignore this slide. So as reported, there's 4 of each. It's much easier to do the math, right? So if we publish that as that, then that's very high privacy loss. But what you could do is you could publish it this way and say, well, the sex distribution is more or less accurate, but the age distribution is off. So this is another thing that we learned in differential privacy, and we actually try to deploy it, is that you can move the accuracy around to different parts while still providing the same privacy loss. So there's another policy decision to make other than what epsilon should be, and that other policy decision is where should the accuracy go? Who gets the accuracy? So you could think of this as an equities argument, but I don't use the word equities because we don't, that's not this community. So there was no off-the-shelf system for applying differential privacy to a national census. We couldn't go out to Costco and buy one. We couldn't go to Google and buy one. We couldn't get one from the academic literature. So we had to create a new system ourselves that would produce high-quality statistics for the more densely populated geographies, right? But for the geographies that are not densely populated, like 5 people living on a block out in the desert, we don't want them to have high quality statistics because that would reveal their private stuff more. But we also needed to create consistent tables because our data users want consistent tables. Strange. So we created a new differential privacy algorithm, and what it does is it starts at the national level, and it does statistics at the national level, and then it does statistics at the state level, and then at the county level, and then down to the tract level, down to the blocks. And as it gets further down, if there's a lot of people, then the statistics are still pretty accurate, and if there's not a lot of people, the statistics become less accurate. That's the secret. So it's not a secret. So our plan is to create this disclosure avoidance system. It's just going to drop right into the census production system. It takes the census edited file, which is red because it's sensitive. We apply this purpleness, and we get blue on the outside, the microdata detail file, which is all synthetic data, right? There's no one-to-one mapping between the people in the census edited file and the records in the microdata detail file. Here's how it drops in. And it gets the privacy budget and the accuracy decisions. So who makes those decisions? Well, in part, it's based on feedback from our data users. There are specific things that this data will be used for, and we have to show that it's going to be fit for use. So differential privacy provides provable bounds on the accuracy of the best possible database reconstruction. What does that mean? It means that the data is going to be as accurate as it needs to be for legal purposes, but it's not going to be more accurate than it needs to be. So there's this public policy trade-off between accuracy and privacy loss, and the data will be accurate enough. And our policymakers within the Census Bureau, the Data Stewardship Executive Policy Committee, which is headed by a presidential appointee, will make the decision, and they'll do that with recommendations from the Disclosure Review Board. If you here at the university, you have an IRB, an Institutional Review Board, they look at the experiment before people are experimented on to make sure that it's safe. And the DRB looks at the data before it gets released to make sure that it won't hurt people, it's safe. And this is a real graph made with our real system that is operational now, showing that as we increase the privacy loss budget, the data accuracy increases. So you probably want to be somewhere around here where there's a lot of accuracy with not a lot of privacy loss. So we inject this formally private noise. It's formally private because there's a mathematical proof about how much noise is needed. And the cool thing here is there's transparency. So we're not just going to explain the details. We're actually going to publish the source code for the disclosure avoidance system. And we're also going to publish code that allows you to take the data from the 1940 census, which is now public, and run that through our 2020 disclosure avoidance system and try it out for yourself if you happen to have enough computer power. Tunable privacy guarantees. The privacy guarantees do not depend on external data, so we don't have that Netflix problem. The reason the Netflix database was re-identified is that they linked it with something called the IMDb, the Internet Movie Database. And the reason the AOL database was made unprivate was that people searched for their own names, and so there was this other database called the phone book that people linked it with. But differential privacy, one of the points of the pretty math is that the guarantees exist independent of external databases. And we're going to be protecting all the members of the population. Like on the old system, we kind of didn't protect the people who didn't get swapped, right? But the protection was you didn't know who got swapped and who didn't get swapped. But now we're actually going to be protecting everybody. So that's better from an equity point of view. So the real challenges are we have to process the entire country at once. The Census Bureau is used to processing things state by state. And every use of the private data must be tallied into the privacy loss budget. And it turns out that this has been really difficult. So if you ever do data stewardship, if you ever have a data set, it's like a really good data set, and everybody keeps wanting to come to you to use your data set, and you want to start tracking who's accessing your data. It's like lending out books, right? And then like you got to be sure you get back the books, and if they made a copy of it and gave it to somebody else, it's like that for data too. So anyway, how the 2020 system works, high-level overview, I've already explained, but we'll go through it again. Every record in the population may be modified, but those modifications are bounded by the global privacy loss budget. And the records in the tabulation data have no exact counterpart. As I said, there's no one-to-one mapping between the records in the CEF, the census edited file, and the records in the MDF. And our explicitly protected tabulations, the ones that the law says we have to produce, will have provable and public accuracy levels. So for the very first time, I can get you better slides. For the very first time, we're going to tell people how accurate our tables are. We didn't ever do that in the past. We just said, here are the tables. And we gave people a measurement error. There was another report somewhere which talked about our undercount or our overcount because we used what's called a dual system estimation to come up with how many people we missed. But we didn't ever tell people how much error was introduced by the swapping. And some of our data users have assumed that there's no error introduced by this privacy mechanism, by the swapping, like that committee. So, but there was error introduced. We just won't tell people how much error was introduced. But now we will. We'll tell people how much error the differential privacy system does. So here's like how it works. You know, we've actually coded two separate disclosure avoidance systems because we weren't sure we would get the good one working in time. So the bad one is sort of like this local model of differential privacy where you put noise on every block. We called that the block-by-block mechanism. You take all the blocks, you run noise, and you get 8 million blocks with noise. Don't do this. So this is the top-down system that we're so proud of. We take our 330 million records. That's a guess. We'll have to count to find out how many people we actually have. We add noise to the national histogram, and we create a noisy national histogram. Now, all these epsilons get added up because it's differential privacy. And the way I like to explain this is that there's a noise barrier. And there's the red data on the left. That's the private data. And there's the blue data on the right. That's the privatized data. This is the safe data. Whenever you go across the barrier, you have to get noise added. So then we take our state level measurements, we add noise to them, we have 51 noisy state measurements, and then we take this national histogram and we distribute it to the 51 states. We do the same thing at the county levels. There are 31, 42 counties. They all get a little bit noise in their true measurements, and we distribute the data down. We keep doing this down to our 8 million habited blocks. We actually have blocks in the census geography that are not habited. You don't want to live in any of those blocks. They're like in water. Don't ask. Geography is really complicated. So there are two public policy choices. What's the correct value of epsilon? And where should the accuracy be allocated? So here are the graphs. So this is the top-down algorithm on the 1940 data, right? And so this is the privacy loss, and that's the accuracy. And in 1940, they didn't have census tracts. They had enumeration districts. And so this is showing that the accuracy on the enumeration districts is pretty bad with low privacy loss. But if you have lots of privacy loss, the accuracy gets better. But at the county level, it's really good. And at the national and state level, it's really good. This is, yeah.
0.94 on the bottom left.
Yeah, that's a 0.94. So I guess even 0.94 is still pretty good. But that's also not zero. Then this is the block by block level, or here it was district by district. So you can see just looking at the two, you're better off with a top-down algorithm than the block by block algorithm. And that's even true when you look at just the enumeration districts. The top-down algorithm does better at every point until there. And at the national level, it's just better everywhere. So we ended up doing 28. We were originally thinking of doing 2018 with the block by block level, but we did it with the top-down model because we got it done in time. So managing the trade-off. So my boss, John Abau, the chief scientist, he has this great article in 2019 American Economic Review where he looks at how do you set that level of epsilon. So I gave you one way of setting it, which is you make the data as accurate as it needs to be and no more accurate. And that works for some applications. But for other applications, there really is a trade-off between the privacy loss and the accuracy. And so another way that you can get at this if you're an economist, anybody here an economist? Nobody. Okay, so that's fine. Sorry? I didn't see it. Okay, one. So you look at the marginal social benefit and you weigh that off against the marginal social cost. And the way he did that in this paper is that they looked at allocation of federal funds using data at the school district level, and the marginal social benefit is that the money gets allocated properly, and the marginal social cost is that people are subject to identity theft. And so doing that, they actually found a correct value of epsilon for that data set, which is pretty cool. So the problem, so this is that curve again, privacy loss versus accuracy. This is the way we're trying to teach everybody to present their differential privacy curves. This graph itself, I've showed you, this is dependent on the production technology. As you get better and better differential privacy mechanisms, that curve moves up and to the left. So we want it being up and to the left as much as possible. But where you are on that curve depends on your social goals when you make the marginal social benefit equal to the marginal social cost. So the problem is that the computer scientists want that number here, and the data users want that up here, because the data users want the data to be as accurate as possible, and who cares about the privacy loss? And the computer scientists want epsilon less than 1, because it makes the math easier. No, I'm not being fair. They want it less than 1 because they believe that, I'm sorry? It's fair. They wanted it less than 1 because they were interested in privacy. But why 1, right? Well, because e to the minus epsilon is approximately equal to 1 plus epsilon when epsilon is small. So basic principles, we've gone the wrong way. So the choice problem for redistricting tabulations is more challenging. So it turns out that the data are used for enforcing the Voting Rights Act determinations. The data that we publish will be used by the Justice Department to evaluate redistricting plans. And so living in the 21st century as we do, we forget that in the early part of the 20th century, legislative districts were actually different size, not by geography, but by people. And there were some legislative districts that had lots of people in them and some that just had a few people in them. And it was a rural-urban thing, or it was also a white-black thing. And so people in the rural white people got fewer people per representative than the urban, largely non-white people. And the Voting Rights Act, and also one person, one vote, ended that. And the Justice Department will use the population data that the Census Bureau publishes to evaluate redistricting plans. So the data have to be good enough for that, right? That's one of the primary uses. It turns out that the racial data is also used for that, or the language data. So there are privacy, and well, the racial data and the language data, I guess. So there are privacy interests based on the Title 13 requirement not to publish exact identifying information, and there are public policy implications that come up when you make available detailed race, ethnicity, and citizenship data. So DCEP has to balance that. So there's more data more background on the 2020 disclosure avoidance system. I gave their better formatted slides, which are on the Census Bureau's website. There was a discussion of the top-down algorithm versus the block-down algorithm at KDD 2018, if that means anything to you. There was another talk. But what's really cool is we have this ACMQ article that came out, and it was just in the current, or it's in the next ACM Communications, where we actually show a hypothetical census block with like 11 people on it, 9 people on it. And we show how to do database reconstruction, how to build the simultaneous equations and solve. So that's kind of cool. Any questions? Yeah, there.
Where?
Yeah.
Yeah, I think there's going to be a few.
In your data, race and ethnicity create huge numbers of breakdown categories that make privacy much harder to obtain. And I wonder, what value is there in still reporting that data?
So so for those of you who don't know, we use the term race for like white, black, Native American, Alaskan Hawaiian, and Asian. And we use ethnicity for Hispanic or not Hispanic. And there had been we were toying with the idea of making ethnicity just another race category, but OMB, that was not decided. So we're using the 2010 categories. The value is that that's the law, right? That's what we have to do. That data is used for voting rights determinations. There's majority, minority district rules. There's laws, Voting Rights Act about having distributions, and I'm not a lawyer, so I'm going to stop there. But we don't have a choice. We have to publish that. But you could decide that it's inappropriate, and you could contact your representatives and get them to change the law if that's what you wanted to spend your time on. Sure. Any other questions? Sure. Oh, it's fine.
We'll save some for the panel, but
Yeah. So what epsilon did you choose?
Oh, well, so we've actually used
The
differential
suspense is killing
privacy
me.
in 3 data releases now. We use differential privacy in the Opportunity Project, the Raj Chetty work. We used it in something called CBAMS, the Census Barriers survey that just came out. And we have used it in the 2018 end-to-end test. I believe that we've announced sure we've announced. We used the value of 7 on one of them. The researchers were given a value of, I think, the Opportunity Project. It's in the paper. So they could do 3 releases, and they could use that 7 any way they wanted. So they could like do one study, and then they could do another study, or they could use it all at once. But we didn't want them coming back to DCEP and asking for more. In CBAMs, we used a very high value, which I think was like 48. But that was applied in the local model on individual data. So it turns out that using the local model on individual data is a problem because you have to use these ridiculously high values of epsilon. It's what Google discovered with its rapport system, that unless you use very high values of epsilon, the data that you get back are just not usable. And what a high value of epsilon like that means for microdata release is a little different than what it means for general statistics release, but it kind of means that the microdata are easier to identify, or you can build a more accurate statistical classifier using that can learn things about individuals that maybe you didn't want to release. And for the end-to-end test, because the data for the end-to-end tests are really not supposed to be used for statistical purposes, they're only to be used for the purpose of people testing their programs. We just set an arbitrarily low value of 0.25, which is pretty low. The value that we're going to use in 2020 hasn't been decided yet.
Okay, thank you.
So I'm not going to ask the question that I'm thinking, because
Yeah.
it probably would get you into trouble if you tried to answer. Just one comment before I take maybe one more question for Simson. If you have any cards or questions for the panel, Sarah's here and we'll collect those. So if you have anything that you'd like to pass along, please just wave her down. Rachel?
I would love to hear you wax poetic on the policy challenges of pushing differential privacy from just like an idea that existed in theory to an actual thing that is implemented in the government.
So I'd like to point you to a paper. It's 4 pages that we put it out at WPES last fall. And it's called, I think, Issues Deploying Differential Privacy. The biggest issue that we've had is the lack of trained PhDs. It's really, really hard to get this stuff right. The second biggest problem that we've had is our computational infrastructure. It's really hard doing. So the way that our system works with that top-down model, every time after we cross the noise barrier, we have noisy measurements and we have this national histogram. How do you make them work together? Like, well, we use an optimizer, right? We use a commercial optimizer, which is extraordinarily expensive, which we have a license for, but there's a lot of computer power required to make that run, and we end up having to do between 400,000 and 800,000 runs of this commercial optimizer. And in my most recent tests, sometimes it finishes each of those run in less than a second, and sometimes it takes minutes, right? So if you want to finish within that time frame, you now need to have a massively parallel system to run it on, and there's been a lot of engineering that I've been participating in. And then we have the data users, right? So like the data users don't like that we're adding noise to all the data, but they don't know that we've always added noise to the data for privacy protection. But now we're telling them, and they're a little bit more upset about that. Yes, in the back.
Okay, one last question before we move to our panel. Where was the question? I'm sorry. Okay. Can you just shout?
Can you hear me?
Yeah.
Okay, so my question has to do with the addition of noise
Yeah.
data. Are there any kind of ripple effects that will cause for surveys that are based on the census data? There may be techniques to kind of correct that noise, but that's going to have a cost.
So what do you mean by a survey based on the census data?
There's other surveys that's going to be done, already done now, going to be done in the future, that's going to be based on the census data.
Well, what do you mean based on the census data?
I guess that's about how you want to define based on, but there are...
But you're asking me a technical question, so I need to know what you mean by that. So like the American Community Survey uses population counts from the census data to weight the samples in the multi-step probability work. And we have not announced our plans for the American Community Survey yet. It turns out that the decennial census is the most simple data product that the Census Bureau does. We ask each person 10 questions. Everything else is dramatically more complicated. We just ask a lot of people those 10 questions. But the American Community Survey has like 80 questions about your household and 80 questions about each person in your household. It's a huge survey. There's a lot more data there. And the state of the art for making that differentially private is lacking right now. So in terms of using the decennial census for other projects, the population counts will be accurate enough that you'll be able to use it for the purpose of weighting other studies. The data products that are based on the decennial census will be factored into the workload. We recently put out a call in the Federal Register for people to tell us what they were doing with data from the decennial census so we could add those into the use cases, into the workload. One of the things that the optimizer is given is all these intended uses so it can make them all accurate. Most of the responses that we got were not about the decennial census, even though that's what we asked people to respond on.
Let's thank Simson for all of his work and for his wonderful contribution.